Hello. In the previous video, we were cut short while we were discussing about the effect of change of temperature on a particular reaction which has reached equilibrium. So just to recap, in the previous video we had discussed that if a reaction is exothermic, then it is exothermic in the forward reaction. So if on the right hand side it's written that the reaction is exothermic, that means it's a forward reaction that is exothermic. And what you would need to do is write on top of the reactants that that particular side has got higher temperature, or that's the hotter side. And this implies that the reverse reaction is bound to be endothermic. Therefore, the left-hand side of the reaction is at a cooler temperature, or it is cold. Now, using this information, we're going to now look into some of the reactions and analyze the change. This is Haber process, whereby ammonia is produced. Delta H is the energy change or the enthalpy change. The negative sign implies that the reaction is exothermic. Now, as mentioned earlier, if the reaction is exothermic, it indicates that it's the forward reaction that's exothermic. That means that the forward reaction results in heat being generated. Therefore, the right-hand side is at a higher temperature. Left-hand side is bound to be the opposite, which is endothermic. Therefore, the left-hand side is at a colder temperature, or its colder side, endothermic. So if you increase the temperature in this reaction, what would happen? Where would the position of equilibrium move to? So you could pause this video and then come back later to see if you've got the correct answer. If you've just arrived after figuring out the answer, do check your work now. So this is how you should have solved the question. You would have looked into that the forward reaction is exothermic, it's at hot. So if you increase the temperature, the position of equilibrium will move to the side to oppose the change. And the change that you've brought out is increase in temperature. So the reaction would try to oppose the change, and that means it would try to decrease the temperature. It tries to decrease the temperature by moving to a side which is cooler. So it will move to the left-hand side in this case, which is colder, which is the endothermic side. So the position of equilibrium will move to the left-hand side here. So if you used high temperature in this reaction, you would get less amount of ammonium. And if the temperature is decreased, then the equilibrium will move to the exothermic side of the reaction. So let's try this out. Now, this is a reaction whereby you've started off with blue copper sulfate. You would need to heat it in order to break it down. So the forward reaction requires energy. So this side, that's the endothermic reaction. So that means the forward side is at a lower temperature. So this side has got lower temperature than the right-hand side, than the left-hand side. So the left-hand side is at a higher temperature. So if you decrease the temperature here, if you decrease temperature, that means that the position of equilibrium will now move to the side which has got higher temperature in order to oppose the change. So the key thing is it will try to oppose the change, and that will occur by moving to the left-hand side. So the left-hand side will be produced, and therefore the position of equilibrium has moved to the left-hand side, and it has counteracted the change. What about the catalyst? Now, if you think about it, we've got a reaction which is reversible. It's got two parts. There's a forward reaction and there's a reverse reaction. A catalyst just speeds up the rate at which the equilibrium is established, because it speeds up the forward as well as the reverse reaction. And because both reactions are increased by the same rate or the same amount, the catalyst has no effect on the position of equilibrium. It just speeds the rate at which that equilibrium is established. So to summarize, in the previous video and in this video, we've just looked into Le Chatelier Principle, the application of it, how you can change certain factors to change the position of equilibrium. And it's got huge implications on the industry. So if you own a factory and if you're producing ammonia, you could use some of these applications, you could use some of these factors to increase the amount of ammonia that's produced. So in a nutshell, you can change the position of equilibrium by changing the concentration or the pressure or the temperature. It's important that when you change the pressure, you focus only on the gas molecules. You don't look at anything else. When you change the temperature, you need to understand which side is exothermic. Exothermic side would be hot. The endothermic side would be cooler. If you're using a catalyst, will you be able to change the position of equilibrium? The answer is no. So catalyst has no effect. And what does a catalyst do? It only increases the rate of reaction so that the equilibrium is established faster. So this is in a nutshell what we've covered in this video and in the previous video. In the next set of videos, we can look into the applications of Le Chatelier Principle and look into the compromise that is achieved between the equilibrium and establishing the equilibrium, i.e. figuring out how much amount of product you're getting and also the speed of the reaction. So thank you for watching.